And welcome to this. This is a live stream going through the content from the AQA GCSE Paper 2 exam. Now, if you're watching this in the future, I know a lot of you will be, then this is a live stream. I'm going to go through lots of calculations from Paper 2 on the AQA exam board. But this is going to be useful for people doing all GCSE exam boards. So please do jump in if you're from a different exam board. Tell us if there's a difference or anything like that. But this is all about the skills. This is practice today for calculation questions. And I'm really pumped because we're going to go through calculation questions for forces and motions and the waves topic. So they tend to be in the second paper in the AQA GCSE. Some of the questions that you get lots and lots of calculations on. And I'm going to work through loads of worked examples, and I'm going to show you exactly how to set them out on the paper. And I'm going to even show you how to put them into the calculator, and this will be really useful. And as I said, I do often get a lot of people watching in the future, so hello people in the future. Do leave a comment in the chat if there's anything you'd like me to cover, but welcome to those people that are joining now. Let me know who you are, where you're from, and what exam board you're studying, and let me know if this is useful. Now, just to say that the next live stream next week, we're doing Wednesday night as well at 7:30, and we're going to do explain and describe questions. So this one's calculations, and the next one explain and describe questions. And there are also live streams just like this one covering all of paper 1, and I did that way back in November and December, and yeah, you should go ahead and check those out on my channel as well. These are the schedule now. I've got one more after this, which is describe and exchange. Do go back and find the required practical ones, but also the other thing about that first live feed is that I also talk about revision techniques and how to actually prepare for exams, and importantly how to learn from mock exam 1. Now that's a really crucial skill, actually learning what it is that you did wrong in the previous one, and if it's a skills thing rather than a content thing, then you can word them. Yeah, oh great, yeah, lovely to see that. Got a distinction star for physics at college, that's fantastic to hear. Great to hear, many thanks for that. I'm going to go through lots of example questions, and what's going to happen as we go through this is actually they're going to get a bit harder. So stick it out if you find in that actually the first ones seem a little bit easy to you, then they are going to get harder as they go. But what we're going to work through is this decode, plan, answer, check methodology, right? So we're going to work through from top to bottom how to figure out what the question is asking us, how to work out how to go about answering it, how to actually answer it, and then how to check that we've done everything in the question that we've asked. So bear in mind, I won't always reference them, but they'll be there all on the side every single time. And that's the methodology that you want to be going through when you answer a question. This live stream is sponsored by Tassomai, and I want to say a very big thank you to them. You can check them out at tassomai.com. It's a quizzing app which is based on the best evidence of how students learn, and it's used in schools and by private subscribers, and feel free to ask questions about it at the end if you fancy that. Tassomai uses 3 of the top 5 revision techniques, and I talk about those top 5 loads on this channel, so there's loads of videos for you to look at there. It is based on an AI algorithm, and it selects the right questions for you at the right time, and it makes sure you're doing practice quizzing, but importantly it makes sure you're doing spaced revision and interleaving your topics. And all you have to do is do 10 minutes a day, 4 times a week to get a daily goal. The more Tassomai you do, the better your memory is going to get. And what's more, you can use that Tassomai to identify your priority areas. So maybe some of you know that forces and waves are priority areas, and this will be really useful for that. But if you use it something like Tassomai, then you will know for sure exactly where you need to target your revision. With some of those other things, the other 2 top 5 tips are self-explanation and elaborate interrogation. So it's going to work like this. I'm going to introduce a quick thing, going to go through some things. Feel free to pause and read if you're watching this in the future. I'm not going to say everything, but I'm just going to talk, for instance, this one is about resultant forces, and resultant forces are the combined effect of 2 or more forces acting on one object, and we can show them in free body diagrams like these, which just means we're just referring to one object on its own and just the forces on it. So we're thinking about it as a free body. And you have to work out the resultant. So for instance here, the resultant force, which we use this symbol, is 0, and here the resultant force is 8 kilonewtons to the right, because the force to the right is larger than the force to the left. Okay, and this is another example, and what you have to do, especially in the higher tier, you have to be able to do this, is you have to be able to combine forces at right angles to one another. So for example, in this case, you can actually use Pythagoras to figure out what the size of that resultant force is, and you could even use trig to work out the direction, so like the angle. Okay, so here's an example of a question like this. Is just calculate the resultant force on the object in the diagram and state the direction of the force. So all you need to do in this case is work out the difference. That's what that means by calculate the resultant force. Now clearly there is 24 kilonewtons to the left, and there is 10 kilonewtons to the right. So we don't actually need to even go for the calculator in this case. Got it ready, but hopefully we can do this one. 14 kilonewtons. I've so far got just 1 mark because there's 2 marks, and the second command word, that's what you want to do when you're checking your work afterwards, is state. Okay, and state the direction, it is to the left. And they of course would accept an arrow saying that way, mate. Okay, so that's the first one. As I said, they'll start off pretty easy and we'll get harder as we go through. So work done is the next one. This is the next equation that you need to be able to use in the forces topic. Work done is force times distance. Now remember, it's got to be distance in the direction of travel of that force. That's an important idea. And work done just means basically the energy transferred when a force causes a displacement. And there's a common example about work done against friction. That's how come we get heating effects whenever we do any energy transfer. For example, you drive in a nail with a hammer, and the nail will actually get pretty hot, even just with being driven in a few centimeters. So this is the example question. Calculate. They're pretty much all going to be calculate questions. Work done is force times distance, force times displacement. And in this case, this is a straightforward one. It's only worth 2 marks, so you're going to get a mark for substituting in, and always be doing this in this way, that you're writing out your formula, substituting in. We don't need to rearrange in this case because we're asked for the work done. And now we go for the calculator, because even though we might be able to do that with pen and paper, why bother? And type that in there, check that you've put it in correctly, hit the D button, and the answer is 9.45, and that is joules. The unit of work done is joules. Okay, so that's our first one. That is a straightforward calculation because the units were already ready and we didn't need to do any rearranging. We got a mark for substituting though, so even if we put the numbers in the calculator wrong, we'd get a mark for substituting and a mark for our final answer with the unit on the end. The next one is Hooke's law, essentially. Force is a spring constant times extension. That's this equation here. Now, incidentally, if you're watching this in the future, then you will need to memorize these, but this year you will be given a full formula sheet. So where it says memorize and given, you can kind of ignore that at the minute. You just need to be able to select them. And what Hooke's law says is that force is proportional to extension, directly proportional to extension. So if you used twice the amount of force, twice the force on a spring that was obeying Hooke's law, then you would get twice the extension. So double the force, double the extension. That's what directly proportional means. And also in this topic, we talk about you have to have 2 different forces to do compression or tension, and that extension could be a squashing, so a reduction in length, or it could be an extension. And there's different types of deformation. Elastic deformation, meaning an object is going to return to its original shape after that deforming force is removed, and plastic deformation means it's going to stay deformed after the deforming force is removed. So here's our example of that. Calculate the force required to extend a spring with a spring constant of 30 newtons per meter by 12 centimeters. So what data have we got first? We've got a spring constant, 30 newtons per meter, and we've got an extension. They use E in Edexcel, no, sorry, in AQA rather, for extension, which is 12 centimeters, and that we need to convert. So this is getting a little bit harder now because we've got 3 marks worth, and the kind of extra mark here is knowing and being able to convert that into meters. Now centimeters is ones where I suggest you just actually work it out by dividing it by 100, because you're probably quite used to converting between centimeters and meters. 12 centimeters is 0.12 meters. Now you need to do that to get full marks on this, but providing you show the rest of your working out, even if you put in 12 where E is, then you're still going to get 2 of the 3 marks, and that's a really good thing. So 30 times 0.12. Again, don't tax your brain too much. Use the calculator to actually make sure that you don't make any silly errors here. 3.6. And what is that we've calculated? It's a force, so that's in newtons. Okay, I hope that kind of makes sense there. This is getting a little bit harder. It's still pretty straightforward. There's one extra step here. There's one extra mark for showing the examiner that you can convert. As I said, if you did 30 times 12, you'd get 360. And actually, you wouldn't get 3 marks for that. You'd get 2 marks, right? because the one mistake you've made is not remembering to convert. So that's a really useful tip, isn't it? Just knowing that if you show you're working out, you can still pick up those extra marks. Then there's this equation, which is the elastic potential energy, which is a half times the spring constant times the extension squared. And be really careful with this one, because loads of people forget to square that at the end there. And it is just the extension squared, but you're not going to make that error if you go ahead and do it in this way that I'm recommending, which is that you decode, plan, answer, and check. So in this case, it's referring to this graph here. You can actually get given a graph like this maybe. The hard question might be, first of all, work out the spring constant and then go ahead and use that to work out the elastic strain energy. There's loads of stuff here as well, okay? So we're just interested in using the equation this time. So what do we need to do? We need to calculate the energy stored. So that's EE in their algebra. A half times the spring constant times the extension squared. Now we can substitute numbers in, but once again, before we do that, let's go ahead and look at what units we've got. 27 newtons per meter is the spring constant K. That's okay, that can go in. We want newtons, we want meters. Those are our SI units that we use all the time. And 6.2 millimeters though is not quite right. Now here's where I suggest what you do is you use a multiplier, right? So 6.2 millimeters, and the milli means thousandth, which is times 10 to the minus 3. So 6.2 times 10 to the minus 3 meters. Okay, that is our extension. Now here again, lots of people do this and they get to this point and they type that into the calculator and they do not get the right answer because they've forgotten to do the squared bit here. Okay, so you do need to square that extension there. All right, let's go ahead and put that into our calculator now, and just to show you exactly how that goes in. Get used to using this times 10 to the button is I strongly recommend. So it goes in as 0.5, which is the half, times 27 times 6.2 times 10 to the minus 3. So you just use that times 10 button. And now you can just press squared without even doing the brackets, because the calculator recognizes 6.2 times 10 to the minus 3 is just a number. And there we go. That's our amount of energy. So 5.2 basically times 10 to the minus 4 joules. This is a tiny amount of energy, isn't it? But actually, one thing you should do when you check is, does that make sense? That does seem like a very small value for energy. But there are situations where actually we have very stiff springs that get extended by very small amounts. For instance, maybe when we're measuring very small forces, or we're measuring literally the analog button presses on some tiny little buttons like this. It may be that we have a very stiff spring which we want to not deform very far and not take a lot of energy to do so. So don't always presume that it's going to be like a nice round number, but do a little bit of sense checking is very important as well. Okay. Carrying on, we're talking about moments now, and this one typically, especially because it is only in triple science, and if you see it says triple science physics only at the top here, then that means it's only for the triple scientists amongst you. This is a moment is a force times a distance, and this idea that a moment of a force, the definition here, is a turning effect caused by a force and is the product of the force and its perpendicular distance from a pivot. So that means like at right angles, the distance from a pivot. Now these ones are quite straightforward because they're just like seesaws. Okay, we call them fulcrums actually. We also have this idea, so it's always perpendicular. The force is always at right angles to the distance. We also have this idea called the principle of moments, and the principle of moments just states that when something is balanced, the clockwise moments equal the anti-clockwise moments. And if you balance a seesaw, that will be the case. And maybe you're the kid with the higher mass, in which case you need to sit closer to the seesaw to balance out the kid with the smaller mass. We'll have all experienced that at some point in our life, I'm sure. I won't say which kid I was. All right, I was the kid with the higher mass. All right, that's that. Now then, so that's how we work that out, and we can actually work out the moments on one side and use that to work out a moment on another side if we know that our seesaw is balanced, our fulcrum is balanced. So actually, that's the question that we've got here. So it's starting to get a bit trickier here, isn't it? Because now it's worth 4 marks. This calculation. Calculate the size of the resultant moment and state the direction of the resultant moment. So we actually have to do two things here. We have to first of all work out the moment in this direction, that is the anti-clockwise direction. Okay, that is a force times a distance. And we also have to work out the moment in this direction, which is also the force times the distance. And then we have to say, well, which one is bigger and what size is it? And say which direction is that turning the seesaw, the fulcrum. So this is 750 newtons multiplied by 3 meters. Okay, again, it is not worth using your brain to do any type of multiplication or anything. Always stick to your calculator because it's going to make less errors under pressure, fewer errors under pressure than you will. And the unit of a moment, by the way, is the Newton meter. Okay, newtons multiplied by meters. And on this side, I've got 300 newtons multiplied by 3 meters, which, all right, I'll allow that, 900 Newton meters. So what's the size of the resultant moment? That is, resultant moment is 2250, take away 900. (1350) Newton meters. Now, prizes for guessing how many marks I've got so far. Well, I have calculated the size. I'm at this point now, I'm checking. Calculated the size of the resultant moment, and oh look, there's another command word in there. So I've only got 3 of the 4 marks so far, and that's because I haven't stated the direction of the resultant moment. And we can say clockwise or anti-clockwise. It is this direction, it is the anti-clockwise direction. Okay, so that is just the last word we need to get the 4th mark. Okay, hopefully that is helpful. Okay, so that's our first little set. We've got a few sets to go through. Please do pop any questions in the chat. I'll do questions just at the end. Hopefully this is useful to you. We're firing through lots of calculation examples and they're already getting a bit harder. Thank you very much to Tassomai for sponsoring this live revision stream. It's the scientific way to learn, and I'm a head of science, and that really appeals to me, that it's the scientific way to learn. And check out the links in the description if you want to find out more about Tassomai. And one feature of the Tassomai that we really like is the tree, and the tree actually grows as you use Tassomai through the branches, which represent the different sections, different topics of the courses, to the leaves, which represent individual learning objectives. You can quickly identify your key areas, your priorities, and you can target them with focused revision. Tassomai has courses for all the major exam boards in the GCSE Sciences, English, Literature and Maths. And we know that by getting your daily goals on Tassomai, you'll catch up. And we know it's been difficult over the last few years. And remember all of the key knowledge, so there'll be no gaps when it comes to the exams. Find the link in the description to find out more. Or go to tassomai.com, and there is a free trial that I strongly recommend that you give a go on this set of mock exams. Okay, let me know in the chat as well, or in the comments, when your mock exams are coming up, and if indeed you are covering paper 2, what's the parts that you're worried about the most? For a lot of you, it will be calculations in the forces section, but for some of you, maybe you're pretty strong on maths. But knowing exactly what you're good at and what you're not so good at is a really important thing to do when you're a young person studying for exams, so you know where to target that revision. There's no point in spending loads of time on the stuff that you're really strong at. You need to focus on the bits that you need to improve on the most. Okay, let's crack on with this one. This is again, it's physics only, so only the triple science students will need to learn this stuff, which is pressure is force over an area. And they write it in words like this: pressure is force normal to a surface over the area of that surface. And the force normal just means that the force is at right angles to the surface that we're actually acting on. So you don't need to worry too much about that. The fluids, remember, exert a force at right angles to the surface, so we call that a force normal. Now when you're doing these calculations, remember that there's this very difficult unit conversion here. If I take 1 meter squared, that's 1 meter times 1 meter, right? That is the same as 100 centimeters times 100 centimeters, which comes out at 10,000 centimeters squared. It's very important to remember this, because some people think if they've got, I don't know, 100 centimeters squared, then that's the same as 1 meter squared. Well, no, it isn't, because there are far more than 100 centimeters squared in 1 meter squared, as I hope I'm demonstrating here with these diagrams. And then lastly, in millimeters, for instance, they could easily do this. They'd easily give you some dimensions of a surface in millimeters or centimeters, and you need to work that out in meters squared before you go and use it in the equation just here. Now, it is valid sometimes to use newtons per centimeter squared for pressure, but the SI unit of pressure is pascals, and 1 pascal is 1 newton per meter squared. So it's very important that you can convert into meter squared from anything else like that. The way to remember this is, if you've got centi and you're squaring it, think about it like this: you're also squaring the prefix. So centi is 100 of something, and so it's 100 squared is the conversion factor. Okay, hopefully that helps chatting through there. Okay, so here it is, it's a 3-mark question. Calculate the pressure when a 220 Newton force is exerted on an area of 4.6 centimeters squared. Okay, so let's first of all get our equation ready, plan it out now. Pressure is force over area. We recognise we've got a force, we've got an area. That's what we're going to go ahead and do that. Oh, and it does say, look, give your answer in pascals. So we better go ahead and convert, because 1 pascal, remember, is 1 newton per meter squared. So we need to convert centi into meters, and that will be like this. If a centi is times 10 to the minus 2, then centi squared, if you like, will be times 10 to the minus 4. So what we can do then is the area is 4.6 times 10 to the minus 4, or you could write that as 0.00046, which the minus 4 just means 4 zeros before the thing. Okay, make sure you can convert these things, and that's meters squared now. Okay, so now we can go ahead. 220 is okay. We want newtons over 4.6 times 10 to the minus 4. Now we go for our calculator. Use the fraction button. 220 over 4.6 times 10 to the minus 4. We should get a sensible answer. Yeah, really quite big pressure, right? So that is 478. So I'm going to call it 480,000 pascals. Now they did ask for my answer in pascals. I can convert to kilopascals if I want, but they've asked me in pascals. Now in this case, if you did this correctly and you did 220 over 4.6, and you got whatever that would be, you got 48 basically newtons per centimeter squared, you can only get 2 marks. And the reason for that, it's a valid unit that you've used, but the reason for that is because they've told you to give it in pascals. So they're testing if you know to convert to meter squared and that you can do that accurately. Okay, so that's your final answer there. And 1 pascal is quite a small unit really. Okay, so there's not very much. 1 apple over a whole school desk would be about 1 pascal of pressure, so it's not a very high pressure. Okay, this is about pressure in a fluid. Okay, pressure as you go down deep underneath a liquid, for instance, or a fluid like our atmosphere as well. And this is an equation that they actually give you, which is pressure is depth or height of the column, h, so we'll call h depth in this case, times density of the fluid, that's the rho in the middle there, and times gravitational field strength, excuse me. And it's a simple idea really, that the deeper you go, the higher the pressure is. Double the depth, double the pressure. Double the density, double the pressure. Double gravitational field strength, double the pressure. Okay, so that's what this bit's all about here. This is a really nice bit as well, because it also explains where upthrusts are from. So an upthrust is caused by there being actually a higher pressure underneath an object than there is above an object. So overall, there's an upwards action of those pressures, if you like. An upthrust is the force due to a object being submerged in a fluid. What we're going to do is going to use that equation. At the bottom of a column of water, the pressure is 500 kilopascals. The density of the water is 1,000 kilograms per meter cubed. Calculate the depth of the column of water. So this is our instruction. Use the value of gravitational field strength as 9.81 newtons per kilogram. Okay, so again, now we go ahead and write out our equation. We're planning it now. H rho g, height times density times gravitational field strength. Now, are our units ready? The only one that's not ready, the only one that's not in SI is pressure. So pressure is 500 times 10 to the 3 pascals. It's 500,000 pascals, 500 kilopascals. And what you can do with kilo, and the only time you don't get rid of kilo is a kilogram. What you can do is just replace it with times 10 to the 3, or indeed just replace it with 3 zeros is also totally acceptable way to do that. Now, the way I'm always recommending to do this is to put your numbers into the equation first. And the reason for that is because there is a, excuse me, I'm going to calculate the depth, so that's going to be h. The reason for that is because there is a mark for correctly substituting into an equation. Density is 1000, g is 9.81. And now we can do our rearranging. So we've got, over this side, we've got times by 1000 times 9.81. So when we move that across, we're going to get 500 times 10 to the 3 over 1000 times 9.81, oops, 9.81, and that is going to be our height. And that's where it really comes in handy now to use our little fraction button, so we can be sure that we're getting our order of operations correct. Fraction 500 times 10 to the 3 over 1000 times 9.81. Okay, now what's the depth of the water then? It's 51 meters. Okay, it's 50.9 blah blah blah. We can round to 2 sig figs unless it tells us something different. It's 51 meters. Okay, so why is that worth 4 marks? Because there's a conversion and there's a rearranging. So hopefully that's a very useful thing for you to do, especially when you're checking your answers. Is this really done enough for these marks? Next one then, this is about our simple describing motion. Up to now we've pretty much been describing forces, right, which are the reason for motion, but now we're talking about motion itself, and this is speed. Speed is a rate of change of distance. Now speed is a scalar, okay, it only has size. I'm going to talk about velocity in a second and how that's slightly different, but it's an example of a scalar. It's really useful, by the way, to know some rough general speeds, because you can use that to sense check your answer. So walking is about 1.5 meters per second, running about 3, cycling about 6 meters per second, you know, and a rule of thumb is if you double these, or times 2.2, a bit more accurate, that would be miles per hour. So walking is about 3 miles per hour, and it's about 1.5 meters per second. So think about doubling. A really fast train would be 90 meters per second, it would be up to about 200 miles an hour. Speed of sound is 330 meters per second, is somewhere in the region of 600-ish, up plus than that, miles per hour. Okay, now the simple equation, as you probably know already, is speed distance over time. That's something you should really know. But also we've got this other equation. Average speed is total distance travelled divided by total time. So no matter if you sped up or slowed down, the average speed over the whole journey is total distance divided by total time. And that's an example of non-uniform motion where the speed and direction might actually vary. This equation again is a 3-mark question, so it's probably something other than just plugging in the numbers. Okay, so let's go ahead and do that. I'm actually going to in this case is the one time I'm going to write out, because I know that some people get confused with these things. Speed is distance over time, because we use v for speed and s for distance. So I just want to keep this one simple initially, but we do use v for speed as well as velocity. Now let's have a little look. So this is 400 meters per second, that's the speed. We're actually calculating the time, so we're going to write in time here. And the two air bases are 600 kilometers apart. So before we actually put that in, we should convert that 600,000 meters. And now I'm going to rearrange. Now this is the trickiest rearranging step that you can do in GCSE. When you've got on top of a fraction, you move it to the top of a new fraction. It's the best way to think about that, I think. So 600 times 10 to the 3 divided by 400 gives us the time in seconds in this case. Okay, so now we reach for the calculator. Again, you see how I don't have to think much because I just have written it down. Now I'm just typing in the numbers, and I can actually check as I go that I'm actually typing it in accurately, which is really useful, right? And it's 1500 seconds. Oops. Okay, that will be absolutely fine. They haven't said exactly what unit they want. But this is 1500 seconds. They might ask you for minutes, okay, so maybe divide that by 60. you can certainly do this if you want. That's also 25 minutes. Okay, and then if you wanted hours, you could divide by 60 again. Okay, and so on. Let's rock on. A really nice comment there, thank you, Tommy. Yeah. Well, waves, we're going to do a little bit of waves calculations in a minute if you want to stick around for that, buddy. Okay, then the distance-time relationship, then this is talking about really distance-time graphs. Okay, so these are all examples of distance-time graphs. This one, and one thing they can do is give you these graphs and then ask you to take numbers from them and do calculations. Now, importantly, the gradient of a distance-time graph is the speed. Okay, so this is a steeper gradient at 1, so it's a higher speed than 3. Also, number 2, this is stopped. Okay, these are here, but these are all constant speeds. Whereas this one, this graph down here, is a curve, and actually what's going on here is this thing is actually speeding up as it goes. And the way to work out speed at a point is to draw a tangent. And the way to draw a tangent is to lay your ruler on it and check that equal distance either side, you've got equal distance from the line, and that should be the same gradient as the curve at that point there. And if you work out the gradient of that, you've done distance divided by time. Look, so you've got the gradient. We do use a large triangle, by the way, in physics, not a tiny little triangle that they've probably taught you how to do in maths. Now this is slightly different, because if we wanted to actually show that things can go backwards, that actually speeds can also have direction, then that turns them into a velocity, a vector, then you can do a displacement time graph. But the rules are the same. However, at point 3 now, the displacement is negative, and so you get minus a number divided by time. Right, so let's have a little look at that. Calculate the velocity, which means direction matters. It's speed with a given direction. It's a vector of the object in the graph. So the displacement, the change in position, if you like, is 19 down to 0. So that is actually it's a minus 19 meter change in position. And the time is 144 seconds. It started at 0, it's gone all the way to 144. So what do we need to do? Calculate velocity. V is s over t. Now here's, as I said, it gets a bit confusing. S we use for displacement. Okay, it means space basically. So don't get confused with that and speed. And now calculate the time. Well, no, not quite yet, because we've got to get our mark for substituting in to make sure that we do that. You know, it's really important, guys, to get that mark, because even if you make a mistake now, or you just don't round correctly or anything like that, make sure you've got the blooming mark for substituting in on the papers, please. They could make the difference between a grade. So minus 0.13 is good enough. It would be 132 meters per second. Okay, so there we are. I haven't put how many marks this would be. This would probably be worth 3. Mark for reading off the graph, mark for 0.13, and a mark for the negative. Okay. The next one is acceleration, which is also an example of a vector, because you can have a negative acceleration. Direction matters. Now this is a velocity time graph, and it's super important. Whenever you recognize, oh, I've got a motion graph, the first thing you do is check which graph is it that I'm looking at, because the rules are different. And every single time I teach this, I say what's going on at 2, and every single time I teach this, somebody in the class says stopped. Okay, it hasn't stopped there. The y-axis hasn't changed during that bit, during 2. And if y-axis has velocity, then at 2 there's no acceleration. Okay, so there's a constant speed at 2, constant velocity if you like. Okay, and here we are then. Again though, 1 is a steeper bit than 3, so 1 is a higher acceleration than 3. And the other difference is that 3 is a negative acceleration as well. There's one more thing you have to do if you're on the higher tier, which I bet most of you watching this will be. Then you also need to be able to work out the area under the graph, and that gives you the distance travelled over the whole journey. And the best way to do that is to actually divide it up into sections, triangle, a square and a triangle, or you could go ahead and work it out as a trapezium if you were feeling really snazzy and wanted to do it in a wanna. Okay, hopefully that helps. Remember, first things first, always be checking which graph is it we're talking about here. And then think through the validity of what you've said. If you've said this is stopped, and it actually has a non-zero velocity throughout that time, well, it isn't stopped, is it? Okay, so there's 2 ways to put this same equation. Acceleration is final velocity take away initial velocity over time, or, and it is the same thing, acceleration is the change in velocity over time. And we use the little triangle delta to mean change in whenever we've got that. So acceleration is change in velocity over time. Here we are, calculate the acceleration. Again, it's been given on a graph, so acceleration is change in velocity over time. What's the change in velocity? It's gone from 14 down to 7 meters per second. So the change in velocity, v minus u, is 14 minus 7 is minus 7. It's not 14 minus 7, sorry, it's 7 minus 14, because the final is 7 and it started at 14. So the change in velocity is minus 7 meters per second. It's a negative gradient, so you know it's going to be negative. And the time it took from 0 to 30 was 30. So now we can substitute those in. Minus 7 divided by 30 gives us, calculate time, minus 0.23333333, but do some rounding. This is minus 0.23 meters per second squared. Please don't be going ahead and using the recurring symbol. We're not interested in seeing that in physics. Do some rounding and do it accurately. Okay. Similar idea. Mark for reading the numbers off. Mark for 0.23 and a mark for negative. Here's one of the hardest bits of calculation in the entire GCSE, which is the equation of uniform motion. But it doesn't need to be all that hard, as long as you follow the step-by-step nature of substitute your values in, simplify, and then rearrange where possible. And this is just to say, I actually said this last time, didn't I? You can add up the areas underneath the graph. And just to say that there's a difference between saying decelerating. When we say something is decelerating, we tend to mean its velocity is decreasing until 0. Whereas when we talk about a negative acceleration, well, that negative acceleration can actually keep on accelerating past 0 and have a negative velocity. So that's the difference here. And this equation says v squared, which is the final velocity, equals u squared, the initial velocity, plus 2 times acceleration times the distance. You'll sometimes see it written as, just do it here, v squared minus u squared equals 2as, and that's exactly the same equation. And there are lots of times in using this equation where either v squared or u squared is 0. So you know, don't forget that it's, you know, they'll often tell you has gone to a stop or starts from rest or something like that, and you'll know that one of those is 0, and so you can kind of ignore the other one. But be disciplined, put your numbers in, rearrange. Let's have an example. Calculate the acceleration which a roller coaster car travels 75 meters as it accelerates to 30 meters per second from rest. They've been kind to us, they know we're going to have to use SUVAT, the equation of uniform motion, so they haven't given us a unit conversion. That's nice. Okay, what's the different values then? It starts from rest, so that's u is 0. It travels to 30 meters per second, so that's v. Okay, and its distance s was 75. So let's put in the numbers we know. 30 squared equals 0 squared from rest, so initial was 0, plus 2 times the acceleration, which is the value we want, times by 75 meters. Okay, now we can simplify where we can, so now's the time to go to the calculator. Let's just do 30 squared in the calculator. And I know, and if some of you are very confident, then you can go ahead and rearrange before you do this, absolutely, but I would stick to this. 0 squared is 0, so we can now just ignore that bit. Times 2 times 75, what's 2 times 75? It's 150, 150a, so that just simplifies all that jazz. Okay, and now you can all rearrange this. So this is the final mark. A equals 900 over 150. So the acceleration is 6 meters per second squared. Okay, again 4 marks, so mark for substituting. Again, even if you couldn't get any further, if you can just put the numbers in the right place, you get a mark, so make sure you do that. And then simplification, rearrange for a mark, answer there. Where do you think I got the other mark from? I don't know, maybe that would only be worth 3 marks in this case. It's a pretty tricky one, maybe there's 2 marks in there somewhere. Okay, I'm going to briefly talk through Newton's laws as well, because I think that's useful, especially for understanding forces. Okay, there's 3 laws of motion, Newton 1, Newton 2, and Newton 3. Newton 1 says if forces are balanced, then the acceleration is 0. So not that it won't move, but that it won't change its motion, that it'll keep going in the same speed or direction, speed and direction. Newton 2 is if there is a resultant force, then the force is proportional to acceleration. This is actually expressed best as an equation. Resultant force is mass times acceleration. And Newton 3, actions have equal and opposite reactions. Now the reason why I like to draw these pictures is because Newton 3 has nothing to do with Newton 1 and 2. And actually Newton 3 is the only situation where there are two bodies involved. And that's because you can actually cause an acceleration. If you push off something, then you will cause an acceleration on yourself. It's because it pushes back on you. That's the reaction. And that reaction is only one force on you, and therefore there's a resultant force on you, and therefore there can be an acceleration. So Newton 3 is also equal forces, just like Newton 1, but the difference is that they're on different bodies. And that means that there can be a resultant force, there can be an acceleration. So there's a little bit more about Newton 1. It's sometimes referred to as the law of inertia, and inertia is the tendency of objects to continue in their state of motion, either at rest or in a certain speed and direction, uniform motion. Newton 2 is about the resultant force is equal to mass times acceleration. And this is the equation we're going to use in a moment, and it actually gives rise to our best definition of mass, really. Which, you know, matter is the amount of stuff. It's not a great definition, is it? But inertial mass is a measure of how difficult it is to change the velocity of an object. So it's actually force divided by acceleration. How much force for each acceleration? That's a really good definition of mass. If you've got a bigger mass, you need a bigger force for the same acceleration. And lastly, Newton 3. And some examples of this: if you push on the ground pushes on you, so the ground actually accelerates you, you accelerate. Another example is a rocket. If the rocket pushes hot gas backwards, then the hot gas pushes the rocket upwards. Okay. So here's calculating acceleration. This is as tricky as I could think they could possibly give it to you, because they've given you the forces on a free body diagram first of all, and they've gone ahead and made some tricky unit conversions. And this is the pretty trickiest one, actually, unit conversion wise. So the first job is to recognize, I need to work out the acceleration. I've got some forces causing acceleration, so I'm going to use Newton's second law, F equals ma. I need to work out resultant force, so the first thing to do is to work out that resultant force. And even if you've just done that, 22 take away 10 gives you 12 millinewtons, then you've got yourself a mark. You at least worked out that you need to use a resultant force. If you use 22, incidentally, you probably get 4 out of 5, even if you did the rest right, but you just missed that first one. The conversion is hard for the mass, because it's 14 micrograms, okay, and that 14 micrograms is 14 times 10 to the minus 6 grams, which is 14 times 10 to the minus 9 kilograms, and we have to use mass as a kilogram in our equations. And also you've got the force is in millinewtons, so let's actually convert that into newtons. 12 times 10 to the minus 3. Okay, kind of gone off the edge there. Now we can put our numbers in the equation. Again though, even though it's pretty tricky, we're still using that same methodology of putting the numbers in where they go. 12 times 10 to the minus 3 is the force. The mass is 14 times 10 to the minus 9 times by the acceleration. Now rearrange 12 times 10 to the minus 3 over 14 times 10 to the minus 9. And you don't need to see it as being standard form. You don't have to 1.4 times 10 to the minus, would it be minus 10? You can just use it as a multiplier. Okay, that'd be 1.4 times 10 to the minus 8, wouldn't it? Okay, so don't confuse yourself by actually having to think that through. You can just use the multipliers of the units. So 12 times 10 to the minus 3, there is in the calculator, over 14 times 10 to the minus 9 equals 857 000, let's go with that, yeah. 860,000 meters per second squared. A really high acceleration, but it's a tiny little mass, isn't it, with a sort of actually reasonably sized force. Okay. Momentum next. Momentum P is mv, momentum is P. Mass times velocity. It's the product of mass and velocity, essentially. A good way to think about it is thinking about how hard is something to stop is its momentum. Calculate the velocity of a 1.5 ton car. Little t means ton, and that means 1,500 kilograms. 1 ton is 1,000 kilograms. It has a momentum of this. Okay, give your answer to two significant figures. Aha, there's another one. There's another mark in here, isn't there? So P is mv. And later in the paper, you will get fewer marks for things like unit conversions, incidentally. Put the numbers in. Mass is 1,500. We want V, I believe, yeah, we want the velocity. So 25000 divided by 1500 is V. And see how we don't need to necessarily say the numbers. We can just, 666, right, that's going to go on forever, isn't it? Now what we must do is do some rounding. And happily, I think I've got this calculator set up so it doesn't give me the little dot on top. We want to get this rounded to two significant figures. Lots of people will make the mistake on this type of question and give it a 16 because they'll just think, oh, that's the two significant figures means the first two figures. No, you need to make sure you're still rounding your figures here, okay? And that's the last mark. If you got 16.6 recurring, you would only get 2 of the 3 marks. And even if you got 16.7, you would only get 2 of the 3 marks because it's asked you specifically for a number of significant figures. So there's a mark for testing that skill. And incidentally, even if you got the answer wrong, and you showed that you could round your answer to that number of significant figures, then you would still get that mark. That's why it's always worth showing you're working out. Okay, let's crack on then. We're almost through the forces stuff. This is momentum, and this is the law of conservation of momentum. And it's the idea that the total momentum before an incident or collision is equal to the total momentum after that situation. So here's one example. Maybe one object is moving, this one, and the other object is at rest, okay? And what they're going to do is stick together and move as one object afterwards, okay? Or maybe both of them are starting at rest, and afterwards they're both moving away from one another. So the initial momentum was 0, and they have equal but opposite momentum afterwards. Or a really difficult one would be that they actually collide and then move away from each other. And what they're going to do always is they're going to give you sort of 3, well, rather I should say all of the information in this equation apart from one thing, and ask you to work that out. So this is a good one to remember. The total momentum before of two objects is mass times initial velocity of one times mass times initial velocity of the second. That's before. Now often you're going to get a mark actually for calculating before. You make that equal to after. This is mass times final velocity of 1 plus mass times final velocity of 2, and the mass is never changed. So let's try and apply that then here. Okay, so here's a situation where we've got one trolley moving with an initial velocity of 4 and one trolley stationary. They both luckily got 1 kilogram mass here. So the total momentum before is 1 times 4 plus 1 times 0, which is of course 4. So the total momentum before is 4 kilograms per meter. 4 kilogram meters per second, and that will get us marks. And actually then we need to use the principle of conservation of momentum to say afterwards it's also 4 kilograms per meters per second, and that equals the final mass, well, this new mass, which is actually stuck together in this example, mv, multiplied by the velocity. And because they're 1 kilogram plus 1 kilogram, this new trolley, this new object, has a mass of 2 kilograms. So all we need to do is 4 kilogram meters per second divided by 2 gives us a speed of 2 meters per second. Let's try and do one worked example of that then. Two cars are involved in a head-on collision. Okay, so the two cars are going towards each other. I'm going to draw myself a little diagram to help me understand what's going on here. The masses of the two cars are shown on the diagram. No, they aren't. They're written in the question in this case. Both cars were traveling at a speed of 15 meters per second. One car has a mass of 1,500 kilograms, and the other one has a mass of 1,200 kilograms. After the collisions, the two cars moved as one mass. Okay, so they're stuck together. Calculate their speed after the collision. Now they are going to be moving in this direction. Okay, it hasn't asked me for the direction, but they are going to move in this direction because there's more momentum that way than there is the other way. So, but that is not important. What we need to know is their final speed. What we need to do first of all is work out the initial momentum, which is m1 u1 plus m2 u2. So 15 times 1,500, and I don't know the way around, doesn't matter, does it? Plus 1,200 times 15. Now that is the initial momentum. Just pop that in the calculator there. And check I've got the numbers right, and the right number of zeros and everything. So the initial momentum for 40500 kilogram meters per second. Now probably I've already got like 2 or 3 marks out of the possible 5 there. This is a really tricky one. This is a 2-step calculation because now I need to use that number, and in a 2-step calculation you need to use the number to work something else out, right? So they're stuck together now, so the new mass of this combined thing is actually going to be 2,700 kilograms, and momentum is mass times velocity, so we just need to divide this momentum by the new mass to give us the new velocity. So V is 40500 divided by 2700. Boom. Also, apparently, 15 meters per second. Okay, there we are. That's a coincidence then. Cool. Okay. Now I have actually done something wrong there, haven't I? That isn't a coincidence because I can't possibly have that much speed in the other direction. Where have I gone wrong here? Yeah, it's because I've forgotten that one direction is negative. Okay, so actually the initial momentum, because momentum is vector, is 15 times 1500 take away 1200 times 15. So let's go back to this now. I would even have got marks for that bit because I'd have shown the examiner that I can actually work out a momentum, and that's part of the question. 15 times 1500 take away 1200 times 15. Now I just want to double check that everyone followed that. What actually happened there is we need to make sure that we're treating velocities as vectors, so we're having negative directions at times. The total momentum of this thing is the momentum in one direction take away the momentum in the other direction. Okay, so now that's much more sensible. kgm/s, and then I'm going to do the momentum divided by the new mass, which is 2700. .66666 recurring, so 1.7 meters per second. Now, hopefully you get the point of doing that. If you work in this habit of checking, hang on, that doesn't make sense. Surely it's not the same velocity as the start. That can't be the case, can it? It's not as if one had no momentum at all. So it's well worth working through this step by step to make sure you get to that stage where you can actually check your own work to see if it makes any sense. The resultant forces cause a change in momentum, and this is another way of writing Newton's second law, which is Newton's second law is F equals ma, right? But also A is delta V over T, so you can substitute that in instead of the A, and that makes a new equation, which is force is mass times V over T, or force is mass times velocity over time. And which actually we're talking about a change in momentum, a change in velocity, so it's force is mass times change in velocity over time. It's a really useful way of describing how safety features on cars work. Okay, here we go. This is a constant 12 Newton resultant force applied to an object of mass this. Calculate the change in momentum of the object. So if a force is a change in momentum over time, then we need to just substitute those values in and work out change in momentum. 12 newtons is change in momentum, that's what we want, over t. They haven't actually given us enough information then. I haven't actually given time here, so there we are. I will cut this one out later on. This will not give us a change in momentum of the object in this case. So anyway, we'll just leave this one. This question is not quite right. moving on. Back to Tassamai briefly, and then just the wave stuff after this. Okay, so thanks for Tassamai for sponsoring this revision live stream. Tassamai is the scientific way to learn, and as a head of science that appeals to me, and feel free to ask questions about Tassamai in the chat or in the comments after this live stream. Tassamai uses AI to target the areas you need to develop the most in order to master the content for your GCSEs, and Tassamai gets to know you and make sure you keep practicing your priority areas until you can't get them wrong. And I use Tassamai in my school, and we use it to make sure that students have memorized the key content for their exams. We trust it because it's based on the science of how people learn, and we know we can rely on students who can complete just 10 minutes of Tassamai 4 days a week to get all the recall questions right in their exams, and they remember all the key facts to help them lower the cognitive load of the harder questions. You might be able to get Tassamai through your school, but if not, you can always set up a private subscription on the website, and you can also try the 7-day free trial. I strongly recommend you give that a go for your mock exams. So let's go ahead and do waves. Then there's not as many calculations in waves. One thing about forces is there's so many calculations, it makes it a really challenging topic. So the first thing to talk about with waves is the different quantities, and they're shown on these diagrams here. So the wave speed is the distance it travels per second, so it's the speed of the wave. Frequency is the number of waves per second. Wavelength is the distance from one peak to another, or the distance from one point on the wave to the same point on the next wave. And notice how I've actually given two different graphs here. This is a displacement versus displacement graph, and this is a displacement versus time graph, right? So in this first one, the time is on the x-axis. So what the distance from peak to peak on this one, on this distance time graph, is actually the time period, which we give capital T here. And we'll talk about that relationship with frequency in a second. And lastly, the amplitude is the maximum displacement of any part of that wave from its equilibrium position. Okay. Now, how does the time period relate to frequency? Well, they're inverse one another, because the time period is the time taken to do a full wave, while the frequency is the waves per second. So all you need to remember, if you've got a frequency, you also know the time period, you just do 1 over. Really straightforward, it's going to be 1 mark. A water wave is a time period of 4 seconds, calculate its frequency. F is 1 over t, F is 1 over 4, therefore the time period is 4 seconds. So the frequency is 0.25 or a quarter hertz. And hertz is the unit of frequency, hertz means per second. Now, other properties of waves, most important equation about waves is the wave speed equation. Wave speed is frequency times wavelength. Okay, this is a bit bump about the practical, but I'm not going to go into that now because I did that with there. Okay, yeah, massive luck to you for your physics Olympiad. Hope it goes well. Stop back and let me know. So this is calculate the wavelength. Wavelength, we use that funny upside down y as a Greek letter lambda. Of a sound wave with a frequency of this and a wave speed of that. Okay, and literally you can just think about that. As long as you know that's V and that's F, you don't need to say the numbers in your head or anything. So put the V where the V goes, put the F where the F goes, and then write in the thing you don't know yet but you want to know. Then rearrange. Lambda equals 330. Copy it down accurately, because copying them down accurately will give you a mark. Okay. Over 440. Again, do these things even when they look pretty straightforward like that. Do them in the calculator, because why on earth not? 0.75, and wavelength is in meters. Okay, over to you. The last one, the last calculation in this, oh no, actually there's another one coming, is talking about ultrasound scanners and different types of echolocation. And this is just an application of the equation distance is speed times time. Okay, but you must remember that the time is for the pulse to get there and back. So it isn't just the time for the pulse to, we want to work out the distance there, distance to a boundary, rather than the distance that the wave has travelled. So here's an example question here. A reflected ultrasound pulse is detected 12 microseconds after it was emitted. The speed of sound in the medium is this. Calculate the distance to the boundary. 3 marks. So here we start with distance is speed times time. Okay. The time is 12 microseconds, so let's go ahead and convert that before we do anything. That's 12 times 10 to the minus 6 seconds. The speed is 240, that's fine. So now we can substitute numbers in. 240 times 12 times 10 to the minus 6. Go ahead and calculate that. Once more, I really hope that you're going to take from this how to use this calculator correctly with the times 10 to the button. Here's our answer. 2.88 or 2.9 millimeters. 2.9 times 10 to the minus 3 meters. How many marks have I got so far? Well, I've done distance is speed times time. Substituted numbers incorrectly, got my correct answer there, but that's the distance the wave has gone there and back. I didn't want that. I wanted the distance to the boundary. So what I have to do finally is do distance over 2 to give me 1.45, if you like, or 1.44 from the rounded form. 1.4 times 10 to the minus 3 meters. Now I know some of you are thinking half of 2.9 isn't 1.4, it rounds to 1.5, but that started life, that 2.9 started life as 2.88, so it would actually round down to 1.4. Okay, next one, EM waves, just to say that this is an example where the speed is 3 times 10 to the 8, the speed of the wave. So I wanted to give you one calculation example using EM waves. Calculate the frequency of a radio wave with a wavelength lambda of 1.3 kilometers and a wave speed v of 3 times 10 to the 8. Again, this is just apply this equation. Wave speed is frequency times wavelength. Put your numbers in where they go. Not forgetting, you want to work out f this time, not forgetting that 1.3, that's 1.3 kilometers, so 1.3 times 10 to the 3. And now rearrange for f, 3 times 10 to the 8 over 1.3 times 10 to the 3 gives me numbers in calculator. Hit the fraction key because we're going to put it in some standard form. 3 times 10 to the 8 over 1.3 times 10 to the 3. Boom. 2, 3, 0, if you like, the 2, 3, 1. Well, I would round to this 2, 3, 0, 0, 0, 0. That would be it to 2 significant figures. Hertz. Okay, let's double check that. Yes, that's right. Okay, let's rock on. Hope that makes sense. Again, that's just handling numbers in standard form. Your calculator treats anything you put that button there and then the number straight afterwards, that it just treats that as one number. It's really useful. Then lenses, I'm not going to go into all the ray diagrams, although I have really good ray diagrams videos where I explain exactly how to do those on my channel. It's really straightforward if you just follow this 1, 2, 3, 4 step by step. Ray parallel to the axis, refract it through the principal focus, step 2, and then a ray from top of the object all the way through the very center of the lens here. And where they meet is the top of the image. So where the rays from the top of the object meet is the top of the image. We're actually going to talk about using this magnification equation, which really, if you think about this magnification equation as just being like a scale factor in maths, you have no problems with it ever. It'll be super easy. Okay. And these are all the different examples of the different ray diagrams they can ask you to draw. Anything to remember is if you're using a diverging lens, you use the backwards focal point. If you just follow that step by step with the rest, you can't make any errors on those. And I've also gone through the details of what the images are like, etc. in this slide. Okay, how to do the calculation then. Calculate the height of the image, that's hi in the equation, produced by a magnification of this, by an object of height this. Okay, so go ahead and write out your equation. Now substitute numbers in. 1.4 times 10 to the minus 4. Height of the image is what we want, and the object is 3.3 meters. Okay, so height of the image therefore is 1.4 times 10 to the minus 4 times 3.3. Which is 4.62 times 10 to the minus 4 meters. Okay. Does that seem a bit small? Yeah, for an image? Maybe. Well, it says a magnification, but a magnification doesn't have to be bigger, does it? It's just a scale factor. So that is a magnification that is far less than 1. And actually, if you're looking at a tree in the distance, that tree is probably going to be, the object is going to be about 3 meters tall, right? Maybe somewhere in that, in the order of that. But the actual image on your eye is going to be way smaller than that. It's going to be less than a millimeter. Okay, so actually that's not, when we're sense checking this answer, that's not a imperceptible, it's not a strangely small actual image. Okay, so trust the maths if it comes to that. Thanks so much for Tassomai for sponsoring this live feed. Tassomai is a quizzing app which is based on evidence, and as a head of science, that appeals to me. It really helps students get the top grades, which is what we're all about here at GorillaPhysics. And we've been talking here about students who've used me in the past and got the top grades. So let's go ahead and rock on for these mock exams and for the real thing, because you guys are going to get some really top grades. If you're here on GorillaPhysics, I'm sure that's what you're aiming for. Check out the links in the description or the pinned comment to find out more. And one of the Tassomai's mantras is that practice makes permanent, but what's more is that Tassomai gets to know what you do and don't remember. And I use Tassomai in my school to make sure that students are focused on memorising the key facts and the key content for the exam. And we trust it because it's based on that evidence. By doing just 10 minutes of Tassomai 4 days a week, you'll ensure you are learning the content in the fastest and the most effective way possible. And when you're revising all your topics, all your subjects, you don't have time to waste on ineffective revision techniques. And if you don't get Tassomai for your school, you can always set up a private tuition, and why not give the 7-day free trial a go? And you can find out more at tassomai.com. Don't forget then, if there's any questions now, then do feel free to whack them in the chat or perhaps in the comments, if you, as I know many people will be watching this recorded in the future. It tends to happen with my live streams. It's a great way to get lots of content out there, but loads of more people watch it recorded, which is great. Over the next, even years later, people watch these live streams, which is absolutely fantastic. Let me know if you're one of those people and how the pandemic worked out, etc. But you can look back in November, where I did some paper 1 live streams as well. I did 3 of those, and I've got one more live stream coming for you next week, which is going to be on describe and explain questions. And that will be from the space topic and the magnetism topic, so I'll be going through some of that content as well. So if you've got any questions about those, do feel free to come on there. If there's any questions in the chat, pop in the chat just now. If not, I've talked for a few minutes extra than I planned to, but I've covered all the equations from the forces and from the waves topic. There's a couple of people talking about, one person talking about the physics Olympiad. Fantastic, very best of luck for that. I hope it goes well. Somebody's said you're a real one for doing this. Yeah, thanks so much to the professional waffler. I guess that's what I've just been doing for the last hour and a bit. And Tommy, thanks so much for talking about how much you've liked my waves videos. Do find my waves playlist if you're interested. I've got some fantastic videos on waves. All right, well, I'm going to say good night then. Thank you so much, and I hope to see some of you. I hope to see all of you next week, and we will go through the describe and explain stuff. And you don't need luck in your mock exams if you prepare well, and the way to prepare well is to go ahead and ensure that you're working on your priorities. There's also a question about primary maths here. Is it free for maths? No, it isn't free, but there is a free trial, and that's the best way to get started. And if you like it after the free trial, then the best way to get Tassomai is to talk to your school and actually go ahead and maybe even take your phone in and say, let you get your phone out for a moment and say, look, I've got this great app, I'm just trying the free trial, but I really like it because it works with AI, and it's the best way to do those. It's the best way to do those top free revision techniques, which is your self-quizzing, your interleaving, and your spaced retrieval practice. Thanks so much, Swiffer. Yeah, nice to have you here on the stream, and we will see you all next time. Thanks, guys.